Hello everyone. This talk is on the advice complexity of the online two-dimensional vector packing problem. My name is Gordana and I did this together with Bengt J. Nilsson from Malmö University, Sweden. I was so excited that I had an opportunity to be a part of this interesting research. I want to begin with an overview of the problem and online setting with advice, and then I'll move on to our online strategies with advice and a lower bound in online regime. So we start with the bin packing problem, and bin packing problem is a well-studied problem, and it asks for minimum number of unit size bins required to pack a set of items, each of at most unit size. In online settings, items are delivered one by one, and each item has to be packed either in an existing bin or a new bin. Our measure of the quality is going to be standard asymptotic competitive ratio. If we speak about online algorithms, then the simplest one is next fit, which has a competitive factor of 2. First fit is similar and has a more complex analysis and therefore has an improved competitive ratio of 1.7. Later on, Lee and Lee show that you can in fact do better using harmonic algorithm. Currently, the best upper bound is 1.57 and there is a lower bound of 1.54. We have almost matched upper and lower bound, but not quite. So let's start with our problem. Vector packing problem is a natural generalization of the bin packing problem to the multiple resource setting, where instead of the single scalar value that you're supposed to pack, you have vectors that you need to pack, and as you add them to a bin, they are not allowed to go over 1 in any of the dimensions. Table 1 summarizes some results for vector packing problem, and for 2D, generalization of first fit algorithm by Gary gives 27/10 competitive ratio, which is best known result. Galambos gives a lower bound of 1.8. In many cases, the online framework is too restrictive, in that it allows an all-powerful adversary to construct the input sequence in the worst possible way for the strategy. To alleviate this, the advice complexity model was introduced, and the strategy receives some bits of advice about the request sequence. These bits are provided by a trusted oracle that has no computational limitation and are written on advice tape of unbound length. The strategy can read bits from the advice tape at any time. And in the analysis, together with competitive ratio, we provide advice complexity. Bin packing with advice received attention in the research community. The first important result is a practical algorithm with 1.5 ratio using advice of sublinear size, proved by Boyer. Later, the result is improved by Angela Puz, and we get something like 1.47. In general, as advice size increases, we can get better competitive ratio. If you have a linear number of bits, you can get one competitive algorithm, but the linear number seems a bit too much. On the other hand, there are some lower bounds on advice complexity, and the best is 1.17 with linear number of bits. So let's begin with our first result by showing a lower bound of 11/5 on the competitive ratio of any fit strategy for the problem. So to construct a lower bound, we need to construct a two-dimensional sequence. So sigma 2 is our two-dimensional sequence, and it contains two subsequences. First is clear, and the second is based on one-dimensional instance. It is obvious that optimum solution of the sigma 1 is equal to optimum solution of the sigma 2. Next, we calculate cost of any fit strategy. First subsequence is packed packed in pairs into 1/2 times opt sigma 1 bins. uh, and they are full with respect to the y coordinate. Then the second subsequence is packed by any fit into at least 17 over 10 times opt sigma 1 bins. That give us a total of at least 11 over 5. On that way, we improved a lower bound for two-dimensional any fit strategy. So, the first strategy is for the instance where all input vectors are restricted and belongs to the green cone that you could see on this picture. The value d depends on the value gamma according to the formula that you have here. As well, we define two other numbers, a and b, but I will tell you later on how they are defined. We define we use five different vector types. A vector is tiny if it has L1 norm from 0 to A, small from A to D half, medium from D half to 1, and large from 1 to B, and huge from B to 2. The advice is the number of large, medium, and small vectors. Then our strategy opens in advance L large critical bins, M medium critical bins, and S half small critical bins. If vector is a huge, a strategy open a new bin and place it. If vector is large, medium, or small, the strategy place it in the first unused large, medium, or small critical bin. And if item is tiny, a strategy use first fit strategy. So we have here a formal theorem of the strategy, and advice is encoded with at most logarithmic n bits, where n is the length of the sequence. It is obvious that from a competitive ratio, our analysis consider two cases. In the first case, the packing does not have any bin with only tiny items, and in the second case, the packing contains bins with only tiny items. And in the graph below, the green line presents a competitive ratio. At the beginning it is 2, and then it grows linearly. Now we will move on to our second strategy, and a strategy is with logarithmic advice, but for unrestricted vectors. And what we are doing here is emulating the algorithm by Fernandez de la Vega and Blucher, which give a p-task in one dimension. However, in two dimensions, when you try to do the same type of bucketing and scaling, you don't get p-tasks, and we prove that you actually get something that you can bound by 2.5. as long as number of buckets in each dimension is even. So we define two types of vectors. Vectors in green region are short and others are long vectors. The value k is a bucketing parameter. And then advice is the number of long vectors in each box. Our strategy serves each vector in the following way. If vector is long, then place it in the bin that is opened by k-scaled vector. And if it is short, use first fit algorithm. So, regarding the second strategy, here we have a couple of results. First, it is easy to see that if k is odd, that any type of scaling algorithm, like the one we done, has to have a competitive ratio of at least 3. To prove it, we define a sequence sigma that could be packed in S bins, but after we scaled vectors in it, there are no two vectors that fit together in a bin. And then optimum solution requires 3 S bins. However, if parameter k is even, then the first lemma says that for sufficiently large k, a scaled solution is no worse than 2.5 times the optimum. That implies the following theorem that says that we can actually achieve a competitive ratio of 5/2 using log n bits of advice with the bucketing parameter that is greater or equal to 640, but it is even. As well, we show that this result is our lower bound, and that is the best we can do even when k is even. So what we show here is that if we combine these results, we have the following corollary. So when gamma is 0, we can use the strategy of angular pose, and that is 1.47. As the angle increases, firstly we use first strategy, and then later on we use second strategy. The figure illustrates the worst case competitive ratio for different values gamma, where red plot is our competitive ratio from corollary, the green plot is what you get using first fit, and brown is our lower bound of 2.2 for any fit strategy. So, to recap our results, we show a lower bound of 11/5 for the competitive ratio of any fit strategy. We also show upper bound spanning between 2 and 2.5, depending on the angle restrictions placed on the vectors given logarithmic advice, where the currently best competitive strategy has competitive ratio 27/10. Interesting open problems include generalizing the lower bound on the competitive ratio to hold for any strategy, establishing a lower bound on advice complexity, generalizing strategy with advice for higher dimension, and establishing more practical algorithms with advice. So, for the end, I would like to conclude by thanking you for your attention. If you have any question, please feel free to ask.